to our course on C-star algebras and groupoids. So I am Karen Strung. And I will be lecturing the first part of the series, starting with the basics of C-star algebra theory. So I think probably some of this, if you were attending Benza and Tomaso's seminar, will be a bit of a repeat, but it's kind of hard to find a useful starting point without doing some Banach algebra stuff. So I will be following this book at the beginning for the most part. I don't know if you can see this. I will put a link up. It's available online for very cheap, but probably you can find it for free if you try. But I didn't say that. Okay, so but you can also look at, there's a book by Murphy, C-star algebra and operator theory, I think it's called. This has more or less the same stuff at the beginning as does Davidson, C-star algebras by example. I think it's called this, all right. Yeah, so if you want a further reading or further information on anything we talk about, I suggest looking at those. Okay, so without further ado, let's start. By the way, if you have questions and you're online, please just unmute yourself and ask. That's probably the easiest way, although Tristan is here as well, and he can probably tell me if there's a comment in the chat. Okay, so chapter 1. Okay, so any course on C-star algebras actually starts with Banach algebras, because a lot of the things you can say at the very beginning, you can say in this more general context. So this lecture and possibly a little bit of the next will have some Banach algebras. So what is a Banach algebra? So a Banach algebra is an C algebra. So all the algebras in this course are going to be over the complex numbers, equipped with a submultiplicative norm. So let's call this A. So by submultiplicative, I mean the norm of A times B is always less than or equal to the norm of A times the norm of B. And we want it to be complete with respect to the norm. Okay. So I didn't say anything about a Banach algebra necessarily having a unit, but if A has a unit, we further require that the norm of the unit is equal to 1. So we normalize when possible. Okay, so some quick examples, what these things are. Examples. We can take a topological space X. And we can look at CV of X, which is going to be functions from X into C that are continuous and bounded. Okay, so we can just equip this with pointwise addition, pointwise multiplication, and we need a norm, and the norm is just the sup norm. Okay, so this is a nice example of a Banach algebra. The next example is somewhat similar. Do I have room on this? No, I better move up. Okay, so let's call this A, I guess. Well, I can start here, B. So now we take X to be a Banach space. And we can look at the bounded linear operators or continuous linear operators. And here, the addition will be, again, just pointwise. For multiplication, we'll take composition of operators. And the norm that we want is the operator norm. And this norm we'll see quite often, I suppose, in this course. So that is just going to be the supremum of Tx. So this is the norm in the Banach space. And we want this to be over all those elements X with norm at most 1. Okay, so this is another very nice example of a Banach algebra. I'm sure you've seen them before. So here's one more example. The one thing I guess maybe to note is that this example here is going to be commutative, whereas this one won't. Here's another example of a commutative one. So if we now take a measure space, then we can look at L infinity. And these will be measurable functions from X to C that are almost everywhere bounded. So we want this, they're greater than this K on just the set of measure 0. Okay, and then we do the obvious point-wise operations, and the norm will be the inf of G equals F almost everywhere mu of the sup XX of GX. Okay, so there's no shortage of Banach algebras out there. Okay, so the next, can you see me if I'm over here? Next up, we're going to talk about spectrum of an element. Okay, so A here will be a unital Banach algebra. Actually, never mind, we don't even need Banach just right away. So let's just take a unital algebra. Again, this is over the complex numbers, and take an element A and A. We say that A is invertible. If there exists some B and A such that AB equals BA equals a unit. So that's not such a surprising definition. And since B, you can check, is going to be unique. If A is invertible, if B is unique. So we denote it by A inverse. Okay, now I will denote the set of all invertible elements in our unital algebra by int A. Okay, so again, A is just going to be a unital algebra for now. I don't need it to be a Banach algebra. And take an element A in A. Then we just find the spectrum of A. Is the set do I have enough space here? So it's going to be all those elements in C such that 1A times lambda minus A is not invertible. So you'll undoubtedly have seen such definitions before, for example, in your algebra. And this is, I guess, just really a generalization. Okay, now here's just an observation. Suppose that A and B are in A, and AB is invertible. And let's call its inverse C. Then you can check that 1A minus BA is also invertible. And its inverse is just, I always forget this, so it should be 1A plus BCA. And I'll just leave you to check that yourself, not so difficult. So that gives us the first thing we can say about the spectrum. The spectrum of AB is the same as, well, I think it was 0. It's the same as the spectrum of BA minus 0. So that's a useful fact to know. Get it backwards here. And will be useful in the following. Okay, so now let's P of Z be a polynomial in one variable. So I'll denote such a thing by the Z. And okay, I'm gonna need some more chalkboard. So I'll make this work hard. Okay, so if we have such a polynomial, then if A is a unital algebra, we can define the polynomial of A just to be PA equals lambda. Did I start with lambda 0? Yeah. Lambda 0 times unit plus lambda 1 A. And this makes sense. It's clearly an element in our algebra. And then we have the following nice spectral mapping theorem. So let A be a unital algebra. And an element of A with non-empty spectrum. Then for any polynomial, we have the following. So the spectrum of this element P of A is the same as the polynomial of the spec of A. So this, of course, I just mean that this is P of lambda, where lambda is in spectrum of A. Oh, there's some things in the chat. Ah, okay. Thank you. Sorry. Yeah. Okay, so proof of this. Well, if our polynomial is constant, then this is fairly clear, so we can assume otherwise. Okay, now let mu be a complex number and consider the polynomial e minus u. Okay, this is a polynomial over C, so it splits. So there exist I should say lambda 0 should be non-zero. Okay, so if mu is not in the spectrum of P of A, then this just means that this will be invertible. And not so easy, it's not so difficult to see that if this is invertible, then actually all of these have to be invertible. So that tells us that this mu is in the spectrum of PA if and only if there's lambda i's are in the spectrum for some I. So let me just squeeze in this last bit here. This means that the spectrum P of A is in P of the spectrum of A. So that's one direction. Maybe I can, fit the rest in right here. Okay, conversely, if we have lambda in the spectrum of A, then we want to look at P A minus P lambda 1A. And we can write this as 1A minus lambda of B for some B. And we know that this is not invertible, so neither is this. So we get the opposite conclusion. Which gives us the result. Sorry, I'm getting a bit hot. So I need to move this thing and move this butter. Okay. Okay. So we have another useful tool here. We have now we need it to be a Banach algebra, so we're going to need completeness. So we want a unital Banach algebra now. and take some element A with norm at most 1. Then (1a minus a), this is invertible. And what is its inverse? Okay, so obviously such a thing doesn't make sense in an arbitrary algebra, but it does in a Banach algebra. And why is that? Well, if we look at the norm, then of course by the triangle inequality, we can bring the sum out. And then by we get this, and then this is now just a regular geometric series in R. So this converges. And hence this guy does, because we're in a complete space. So it converges to some B. So this is a well-defined element. Okay, so we would like to see that this is indeed the inverse as claimed. Multiplicativity. Very hard early in the morning. Okay, so let's see that this is indeed the inverse. Well, that's not so hard. We just need to show that this is equal to 1. And of course, this is just and so if we replace this by some big N, what do we get? We get 1 minus a to the N plus 1. Wait, sorry, should still be a 1. Okay, and we know that A has norm less than 1. So as N goes to infinity, this will go to 1. And of course, we need to check it on the other side, but that's a similar calculation. So sure. Okay, so indeed, by uniqueness of the norm, we get that he is indeed the inverse. Sorry, what did I write? This is definitely not true. I meant to write this. Is the inverse as claimed. Okay, so what we're kind of working towards here is we had this nice theorem over here, but note I had to specify that the spectrum wasn't empty. But in Abanic algebra, it turns out that we don't have to worry about that because that will never happen. All the spectrums will be non-empty. But we need a few lemmas to get there. Erase some chalkboards. So the first is the following. In our Banach algebra, still just considering the unital case, then the set of invertible elements is actually an open subset. And the map that takes an element to its inverse is in fact differentiable. Okay, so let's first show that it's open. All right, so take some A in the set of invertibles. And we want to show that if B is an A and it's sufficiently close, then it's also invertible. And that will be enough to show that it's open. Okay, so how close do we need it? Well, let's take A minus B to be less than 1 over A inverse, the norm of A inverse. Then let us look at 1A minus BA inverse. And we're going to aim at using the last theorem. So what is this? Well, we can take out this A inverse and submultiplicativity. I don't know why I can't say that word, but you know, there we go. Yes, I am in fact a native English speaker even, so it's very embarrassing. Okay, so this is less than 1. So we know that BA inverse is invertible. And a similar calculation shows us that A inverse B is also invertible. So we get that B times A inverse BA inverse. Now we need a B. No, we don't. This is enough. This is equal to 1. And we can also get 1 with B on the other side by doing We need a B here. This should be A inverse, and then this should be A inverse, B inverse. Okay, so you might say to me, Karen, these are not the same elements. And you are right. So this is not actually the inverse of B, but you can play around and figure out just how to write the inverse of B in terms of these things. It's not so hard. So B is invertible as well. Which shows the first part. So this is indeed open. Okay, so the second part of our lemma is to show that this is a differentiable map. Okay, so what do we want here? To show that this map A to A inverse is differentiable. What we need is a linear operator linear map such that for every A in the invertibles, which is where this map is defined, the limit as H goes to 0 of so that's what we mean here by differentiable. So how will we define this? Well, for B, an element of A, define L of B the conjugation by A and A inverse with a minus sign. And then let's take H to be small enough that we have this is, maybe we'll even just do a one over 2 the norm of A inverse. And I'm running out of space again. Okay, so what did we have here? We had the norm of H is at most 1 over 2 A inverse, which means that A inverse H which by the properties of the Banach algebra norm imply this here, and that's at most half. In particular, it's less than 1. So this means that 1 plus A inverse H is indeed invertible with inverse again by the theorem whose number 1.2.4, I guess maybe just the one right before this. Okay, and now what we're trying to, yeah, so let's say 1A inverse H inverse so this is the inverse of that. We can sub that guy in. And what is this? This is just okay, and then we already know an estimate on this guy. So we can just take out this sum and we get a geometric series. So we have that A inverse H and this is then seen to be at most twice A inverse H norm squared. And we can plug our choice of linear map L. Now we're going to plug it in here with respect to H, and this last calculation will give us what we want. So this is all over H. Okay, so I want to take out an A inverse. First I should not get ahead of myself. So what was this? This was A inverse B inverse. H A inverse. And again, this is all over H. So now I would like to factor out an A inverse. So I need to sort of stick it in here and then take it back out. But then that gives us and this is again all over H. And by our previous calculation, we get that this is at most 2A inverse squared H squared over H. Which is at most, well, it's actually equal, I guess, to 2A inverse squared H. And of course, this goes to 0 as H goes to 0. So that completes the proof. So I'm glad they can see the board better. Okay. Okay, just a bit of notation for a moment. So if X is a metric space, then I will denote by BXR to be the ball of radius R around X, the open ball. So and similarly, the closed ball, I'll just put the closure over there, and then it will be distance less than or equal to R. Okay, so we have the following lemma. Okay, so we're going to get a little bit more of a handle on just what kind of elements can be in the spectrum of an element in organic algebra by showing it has to be contained in a ball around the element itself of radius to the norm, of 0 and radius to the norm of the element. So for any A and A, the spectrum is a closed subset of the closed ball around 0 of radius A. So of course, in the complex numbers. And again, we have a map that we can define outside of the spectrum, which will be differentiable. So this will go from complex numbers minus the spectrum of A, the A taking a complex number lambda to the inverse A minus lambda 1. And this makes sense, of course, because lambda is not in the spectrum. Okay, so now if we show that the spectrum is closed, then you can see that this will follow from our previous lemma about the differentiability of the map A to A inverse. Okay, so we just need to show that this is closed. Okay, so I won't go into the details because I would like to get through a bit more, but it's sort of a reasonably easy exercise. So the idea is show that if lambda is strictly greater than the norm of A, then lambda minus A is invertible. So this is a reasonably easy exercise based on all the other things we've shown today. And once you've done this, of course, it follows immediately that this is actually a closed subset. And as I said, the differentiability, oh, I didn't actually write the statement. The differentiability of this map then follows from what we just saw. Okay, so a little bit more notation before the next theorem, which will show us that in a Banach algebra, the spectrum is non-empty. Okay, so I will denote by A star the continuous linear dual of A. So that's going to be functions from F, from A and to C that are continuous and linear. And then we can equip this with the weak star topology. And if you aren't familiar with this, basically it's just the topology of pointwise convergence. So we have that phi n goes to phi, and only if phi n of A goes to phi of A. Okay, and one thing that we'll need to know is that A star separates points of A. So so if we show that we have an element A on which two elements A and B, and they're different on all elements of A star, then A is not equal to B. And conversely, if they're the same, then A is equal to B. So that will come in handy in our proof of the following theorem. Any element in a unitary Banach algebra has non-empty spectrum. And this is not true in an arbitrary algebra. So this is a special feature of our Banach algebras. Okay, so first of all, if A happens to be 0, then the spectrum of A will contain 0. So it's clearly non-empty. So let's assume that A is non-zero. Okay, now for a contradiction, let's assume that the spectrum is empty. Okay, then you can check that the map is bounded on the compact disk of radius 2A, 2 norm of A. Okay, and that implies then that the map from C to C given by lambda A minus lambda 1A, and now we're going to apply some phi in our dual. So we also know that it is differentiable. So by the Liouville theorem, Liouville plus previous theorem, this is constant. Okay, but these are linear functionals, so and this is for every lambda in C. So we get the fact that A inverse is equal to phi of A lambda 1A inverse for every phi in our dual. And as I mentioned, the dual separates points. So that means we get that A inverse and A minus lambda 1A inverse are always the same. In particular, I guess we could take lambda equal to 1. Anyway, that's impossible. So there's our contradiction. So we've reached a contradiction by assuming that the spectrum was empty, which proves the theorem. Okay. So I guess we go to 1, right? Well, maybe I'm doing okay. Okay, so then we have this nice little result that comes from this fact. Suppose we have a unital Banach algebra A. And every non-zero element of A is invertible. Then we must have that A is just the complex number. Which is a perfectly nice Banach algebra with respect to its usual norm. All right, so what is the proof? Take A and A minus 0. Now we know that its spectrum is non-empty, so there exists some lambda in the spectrum of A. Which means that A minus lambda 1A is not invertible. So we must have that A minus lambda A is equal to 0. So A is equal to lambda A, oops, wonky, 1A. And the map that takes 1A to 1 gives us our isomorphism. Okay. So we have a definition, the spectral radius of an element. Yeah, unital static algebra. We'll call A. Is defined to be, so denoted by R of A, and this is just going to be the supremum of lambda, absolute value of lambda for those lambdas in our spectrum. Okay, so we already know that this has a supremum because we know that we're at least bounded by the norm of A itself. So it makes sense. But we can say a little bit more. And in fact, when we eventually get to C-star algebras, we'll see that we have an even nicer characterization of the spectral radius. But for now, what we can say is that for any A and A, we have that the spectral radius is equal to the infimum of all n greater than 1 of A to the n 1 over n, or you can also think of it as then as n goes to infinity of A to the n. All right. Okay, so if we take some lambda in the spectrum of A, then our polynomial mapping theorem that we had earlier tells us that lambda n is in the spectrum of AN. And we know that the spectrum of an element is always bounded by the norm of that element. So we get that lambda to the n is at most A to the n, and hence lambda is at most A to the n 1 over n. All right, so this gives us one direction. So this is for every lambda in the spectrum, and every n greater than 1, which tells us that this radius is greater than or equal to, less than or equal to this infimum. So we need to show the other direction. So we're going to show that this is bigger than the lim sup of the norm of A to the n to the 1 over n. Okay, so we find a subset of the complex numbers D to be the open ball of radius, spectral radius inverse of A, if this is non-zero, and just the whole complex plane if it is. Then if lambda is in D, we have that 1A lambda minus A, 1 minus lambda A is invertible. I have written down here theorem 1.24, so I'm sure that's long been erased, but I hope that that is the correct theorem. Okay, so this implies that for every continuous linear functional, the map f from D to C, which sends lambda to phi of 1A minus lambda A inverse, is analytic. Okay, so this means that it's there, we can find complex numbers such that UDN lambda n for every lambda in D here. Okay, so we have established this, and we know that for lambda smaller than 1 over the norm of A, which is smaller than the spectral radius here, we have that ever useful identity here. This is going to be n in n of lambda n a to the n. So what is f of lambda defined here? That tells us that this is just lambda phi a to the n. And comparing this with what we know from it being analytic, this implies that phi a to the n is Cn. Okay, so this means that since this is well defined, we have that phi a to the n goes to 0 as n goes to infinity. So this sequence is bounded. And of course, we haven't actually used anything special about our linear functional. So this is bounded for any phi in A star, which in turn implies that this is bounded. So again, using the fact that A star separates points. So it's bounded, let's say, by some number we'll call M lambda. And we're nearly done with this group. So that tells us that the n 1 over n is less than this M lambda 1 over n is lambda inverse. So our then soup is at most lambda inverse, and that's for every lambda in D. Which implies the result for our spectral radius. Which is what we wanted. Excuse me. All right, we're pretty much finished this section on the spectrum. But one thing you may notice that was missing is that this was always unital Banach algebras. So what do we do if we just have a Banach algebra that isn't unital? So what we need to do is unitize it to define the spectrum. Am I on the right numbering? I guess we'll never know. Okay, so take a Banach algebra. It doesn't matter if it's unital or not. And we'll define A tilde to be the direct sum of A with the complex numbers as a vector space. And with multiplication, so we have an element A, lambda, and we want to multiply it to B mu, and it should land in here. So we will take AB plus lambda B plus mu A, which is certainly an element in A, and lambda mu as our element in C. Okay, so this is now a nice algebra, which you'll note is now a unital algebra. And we can also define a norm, make it into a Banach algebra by setting the norm of A lambda to just be the norm of A plus the absolute value of lambda. Okay, so you can see that A fits in here nicely as A0, and we get the same norm. So it preserves the norm under this. And we call this the unitization of A. And this allows us to define the notion of spectrum in a non-unital C-star algebra. So if A is an A a non-unital, then its spectrum is going to be all those complex numbers where now we consider A as an element in its unitization. So again, this is really A0 and this is really 0, but that's clear. So just write it like this. This is not invertible. As an element, again, in the unitization. So you can go back and check which one of these theorems also holds for our non-unital Banach algebras. Usually not a very difficult thing to show that most of these things go through. And in the last 10 minutes, I will try to plow through a bit about ideals, which actually is pretty short, so hopefully we can do that. Okay. So if we have any algebra, then we can make sense of right and left ideals. So and these are just closed under multiplication either on the right or the left. And I'm going to call these algebraic ideals so that we can differentiate once we're in the case of a Banach algebra. So we want, am I going to get this in the wrong direction? A, B is in I for every A in I, and B in A should be multiplication on the right, and then to the left, we just want it the other way around. And if I say an algebraic ideal, then I always mean an algebraic ideal that's, so it's both a right and a left ideal. So normally we'll want to consider two-sided ideals. And you can see that when we have a two-sided ideal, just an algebraic ideal, then we can take a quotient and we get an algebra. So we would like the analogous thing in Banach algebras. So and this is with respect to the usual obvious multiplication and addition. Now, if we're in a Banach algebra, then when I say just an ideal, I will mean it to be closed. So if it's a Banach algebra, then we have right, left ideals, and we can drop this algebraic. And again, just an ideal, this will always refer to the closure. So you can talk about algebraic ideals in a Banach algebra, but if I just say ideals, I mean the closed version. It's an algebraic and ideal. and closed. Same thing for left or right. Okay, so in this case, we can equip AI with the quotient norm, make it into a Banach algebra.
Excuse me.
Yes.
You meant a closed ideal there, yeah?
Here, yes. And two-sided. So if I just say ideal, I'll always mean closed two-sided ideal. And otherwise, I will tell you what other information, like if it's algebraic and I don't want it to be closed or left, right. But if I just say ideal, I always mean closed and two-sided. Okay, so this makes into a Banach algebra. And we might want to ask ourselves, when will this Banach algebra be unital? And it will be unital when our ideal is something called a modular ideal. What does that mean? There exists some element u and a such that a minus ua and a minus au are always in our ideal, and that's for every a and a. Okay, so it's easy to see that if a itself is unital, then every ideal is going to be modular, because you can just take u to be the unit here. And you can try to figure out just exactly what the unit of ai will be. So that's a little exercise, I guess. Okay. We have the usual notions in a Banach algebra of things like the trivial ideals. That's just 0 or a itself. Proper ideal, put in algebraic or left or right as you like. This is an ideal that's not equal to a itself. So in particular, if I say proper, I mean it could be 0, but if I say trivial, I'm excluding 0. We also have the notion of an ideal generated by a subset. And that will just be, of course, the smallest ideal containing this set. And maximal, if I is proper and not contained in any proper ideal. Or I guess it should be not properly contained because it's obviously contained in itself. Now, the nice thing about modular ideals is that you can make sense of, okay, maximum modular ideal is defined in the obvious way. And by Zorn's lemma, every modular ideal is contained in a maximal modular ideal. And hence, in a unital Banach algebra, every ideal is contained in a maximal ideal. Okay, I'll just end quickly with a proposition, just so that this wasn't just ending with a bunch of definitions. But I won't bother to prove it. So just so we can see the difference between algebraic ideals and regular ideals. So position. So A is Banach algebra. And I and A is an algebraic ideal. Then if I is proper, so is its closure. Oh, I guess I need modular. And why is this useful? Because this will tell us that whenever we have a maximal modular ideal, it has to be closed, which will come in handy later on. But for now, I'll end there since I've already run over by a couple minutes. So thank you all very much for coming. If you ever have questions or whatever, feel free to email me. And otherwise, see you next Tuesday. Do you remember clapping in lectures? I don't think we did. I think you just sort of snoozed off and ran away.